Typically, you need a dedicated GPU for every large language model you want to serve. That means if you're trying to serve multiple custom models, it quickly gets expensive. So in this video, I'll explain how to serve multiple models on the same GPU, which should save you significant expense. This is useful if you have different customers who need access to separate models. Perhaps they've been trained on different data sets or they are tuned for different applications. The way I'll do this is by using LoRa adapters, which you can think of as clip-ons to a shared base model. We'll load the base model onto the GPU and we'll clip on and off the adapters according to the custom uses that we need. I'm going to describe simple out-of-the-box approaches like Lora-x all the way through to building a custom vLLM server that has automated loading and unloading of adapters. So whether you're just getting started or you want some more advanced techniques, hopefully this video will be for you. So there'll be four parts rather to the video. The first part, I'm going to go over some of the theory fairly quickly of how LoRa works, specifically for inference. And I'll briefly describe the fine-tuning and then I'll cover how it works for inference. Then I'll show you a service that I've developed. It's a wrapper that allows you to make calls to a LoRa model. So you can just set up an API endpoint and you can inference it for your LoRa and it will automatically load your model for you very quickly and give you back a model response. So that's kind of at a high level, and then I'll dig into what I've built underneath and I'll show you two options for what you can build underneath. One is a basic approach using Lora-x, and I'll provide a repository for that. It's a public repo called Basic Inference on the Trelis research organization on GitHub. And then I'll go into much more detail with an advanced implementation where I take vLLM and I build a proxy server that allows me to manage the loading and unloading of the LoRa adapters. And that will be available for those who have purchased lifetime access to the Trelis Advanced Inference repo that you can find on trelis.com, trelis.com. Okay, so let's talk about LoRa serving. And first of all, what LoRa is. Well, LoRa stands for low rank adapters. Rank you can think of as either the height or the width of a matrix. It's technically the number of independent rows, but roughly speaking, it's usually the smaller of the height or the width of the matrix. And the reason why low rank is relevant is because what we're trying to do is when we want to train a language model, instead of update all of the weights, we want to update a smaller subset because that will be quicker and require less computation. So in LoRa training, you start with a model that has already been trained. Maybe it's a Llama 3 8B model, for example, and it will have a lot of weights. It will have a lot of numbers. For example, the 8B model might have about 15 gigabytes worth of numbers, and they will all be contained within large matrices. For example, I have a matrix here that's about 1000 by 1000 in size. And rather than training this entire matrix with LoRa, what we do is we train adapters. These are the clip-ons that are going to sit just on top. And the clip-ons are sized such that when they are multiplied together, here's a clip-on that's 8 by 1024 and the other is 1024 by 8. When you multiply them both, they will result in a clip-on that's 1024 by 1024 and can be superimposed on top of this matrix. But of course, to update these weights, there are far fewer to update because there's just going to be 1024 times 8 times 2 rather than the full 1024 squared. So this is a method that allows us to greatly shrink the number of parameters that we have to train. And it turns out it's also quite effective in terms of performance. If you have data that you use to train this adapter, it actually performs well and sometimes even better than training all of the weights in the original matrix. And the reason this tends to work well is because by training these smaller adapters, we're kind of forcing the knowledge into higher level representations that don't overfit. They're not too granular. You see, when we train with a small amount of data, we want to make small updates to the overall model. And if you try and update every weight, you can achieve overfitting, which means it will perform well on exact examples of your data. But if the questions deviate from your exact data, it can just give you back it can just overfit and give you back examples that are in your data set, which is not what you want. You want it to generalize. So this is very roughly how you do LoRa fine-tuning. There are many videos you can find on the Trelis research channel that will describe how to do this using trainers like Hugging Faces and transformers. But today what we're interested in is the question of, okay, I have a base model. It's a popular model, maybe Llama 3 8B, and I have multiple adapters that are trained. So I have the A and B for, let's say, the rules of touch rugby. I have them for the rules of badminton. I have them for the rules of, let's say, ice hockey. And what I want to do is, according to the user of my application, I want to load the relevant adapter. So if a user with questions on ice hockey comes, I want to just load those adapters on top. Whereas if a user is going to be related to touch rugby, I want to load those adapters. So I want a way where I load the main weights onto my GPU, and then on the fly, I kind of clip on the adapters that are appropriate for that customer. So mathematically, when I say clip on, let's just take a quick look at how this works. Clipping them on essentially means you take the weight matrix and you add on the product of A and B, where A and B, I will refer to them as an adapter, but actually there will be two matrices that are there for every base matrix. And of course, well, not of course, there are very many matrices within a large language model. So actually there are very many sets of adapters. There will be different adapters that are applied to every single layer. But often I'll just say the adapter. And when I say the adapter, I really mean the set of adapters that will be applied to the set of base matrices that are in the language model. And by the way, I say language model, this also applies for vision models. It also applies for diffusion models. So here's again a next level of detail on how this clipping on works. So normally if we've a GPU, let's say we have, it could be an A100, an NVIDIA A100, we have what's called the VRAM, or the virtual RAM, random access memory. And this RAM here is a special type of storage that is deep within the computer and very close to the compute kernels that actually do the computation. And they need to be close because we're going to shuttle a lot of data in and out of the computation kernels. And so ideally, we have all of the information loaded into the VRAM so that we can quickly shuffle in and out and do the calculations quickly. And so we typically load our full model into what's called the VRAM. This is often loaded in shards. So we'll have, say, 15 gigabytes of weights, and we will load them in shards into the VRAM so they're ready for this quick computation. And what we're additionally going to do in this video is we're going to load in the adapters. So if we've one adapter again, say for ice hockey, one for touch rugby, one down here for what was the other sport I said, it could be lacrosse, we're going to load those into the VRAM as well so they're ready. And then based on the request that comes in, we're going to say, okay, let's make use of this adapter here, which is for ice hockey. And let's apply it using that W equals W dash equals W plus A times B. Let's apply it at inference time on the fly so that we can get the custom behavior of this adapter here. So you can see we're going to load in all of the LoRa adapters. Of course, there's going to be a limit to how many we can load in, but thankfully they're small. So these adapters in total are often less than 300 megabytes, depending on the rank. So depending on whether you pick 8 here, or a smaller number, it means you'll have less parameters, or a larger number like 128, you'll have more parameters. But typically each adapter will be less than 300 megabytes, just a few hundred megabytes, whereas large models are typically in the gigabyte range, like 16 gigabytes or 15 gigabytes for Llama 3 8B, for example. So there is a limit to how many adapters we can put in. If we put in too many, it's going to run out of VRAM. We'll just run out of space inside the GPU. So what we do is we set a limit, and you'll see later on, we're going to kick out the adapter that was the least recently used so that we make space for any new adapters we need to load. And I'll talk about that loading in a bit more detail. In fact, I'll talk about it right now. So we'll have a hard drive, which is not part of the GPU, to be clear. We have a hard drive where we can store many more adapters. And as needed, we will load them onto the GPU. So we should have the most used ones ready on the VRAM. And as I said, we'll kick out the least recently used back to the disk so that it can be reloaded at a later stage. And actually, we're going to take this one step further. If you even imagine that your hard drive is now full, and that would really be a lot of LoRa adapters because your hard drive might be a terabyte and your adapters are maybe 100 megabytes. So you could store very many on your hard drive here. But even if your hard drive gets full, we can take it one step further and we can just dynamically download the adapters from Hugging Face. So if Hugging Face has got a repository with tons of our adapters, including private adapters I'll talk about later, we will on the fly just download those onto our hard drive. And then as needed, we'll download them onto our download upload onto the VRAM of the GPU, so they're ready for the fast inference. And because these adapters are quite small, all of this is actually quite quick. It'll take usually less than a second to load or unload. And even to download from Hugging Face, if you use HF transfer, which we will, it can actually happen within even less than a second in some cases. So this is the idea. We have our base model that's shared. We have this big model that's being shared. And then we have these adapter behaviors that are being injected on the fly as we need them according to the request. So next, I'm going to show you how this is implemented in a simple Lora-x implementation. Lora-x is a library. It's built on TGI. TGI is text generation inference. It's a Hugging Face library that allows you to do inference. It's like vLLM. It would be a competitor to vLLM, let's say. They're both open source. And TGI has been modified by a company called Redis into Lora-x so that it dynamically does this for you. So it will manage this caching of the adapters on the drive and will manage downloading them from Hugging Face as you need them. So I'm going to go through Lora-x and I'll show you how that works. And then I'm going to show you how to build more from scratch this loading or unloading behavior. And I'll do it using vLLM, which is probably the most popular inference library. And vLLM actually allows you to dynamically load and unload adapters, but it doesn't yet allow you to manage which ones are loaded and which ones are loaded on your hard drive or not. So for that, we're going to need to create a database to manage the loading, and I'll get to that a little bit later. And then last of all, I do want to show you this service, which is a wrapper that I've built, and it allows people to just make requests to any LoRa adapter for a given base model that's available on Hugging Face. So actually, I think I'm going to start off with the basic example first with Lora-x, built off TGI. Then I'll go through the more advanced example with vLLM, and then I'll show you the service available. It's in closed alpha now, so you have to sign up for the waitlist, but it's available at finetunehost.com. All right, so here is the Lora-x database, or rather GitHub. You can see about 2,000 stars there. And you can check it out for yourself with the documentation. And I have generated a simple example of how to use Lora-x. It's available in this public repo called Basic Inference. You can find it on the Trelis Research GitHub organization. So head over to Basic Inference, and we're going to be interested in the multi-lora folder here, which is going to walk us through some of the steps. So what I'll do is just git clone this with cursor. And this is the advanced inference. Let me see if I have the basic inference. And this is the basic inference. So there are currently two scripts in it. There's basic Postgres RAG, how to build a RAG database using Postgres. And today there's the new edition of multi-lora. So I'm going to cd into the multi-lora folder. In fact, I'm already in there now. Let me increase my screen size a bit. And let's open up the README that's contained within multi-lora. So I'll open up the README right here. And let me just swap my theme into something a bit darker so that it's a bit easier on your eyes. So here we'll start off at the top of the file. This contains scripts for making inference calls to Lora-x. And essentially what it does is it sets up a Lora-x server, which is a Docker image that's been set up by Redis. And actually this is wrong here. It's actually a Redis-based TGI server is the correct way to call it. And so you won't find that in vLLM docs. You will find it using the Lora-x docs on GitHub, or you can use a one-click template here. So if you click on this, it will bring you to a one-click template for Runpod. You can select a GPU. Let's take a quick look actually at the one-click template. Indeed it is. It's in the GitHub repo, and Redis have created a Docker template called Lora-x, and we're looking at the main branch. And here we're going to run the MetaLlama 3.18b instruct model. The reason why I'm using it from Unsloth is just because it doesn't have any gate on it, so I don't have to use a Hugging Face token to access it. And we're just going to launch it on port 8000, which means we need to expose port 8000 here, and then we'll be able to hit that server, which will be a TGI server. There are also, well, there is one environment variable to set. It's this HF hub enable transfer. And if you set it to 1, it will allow for fast Rust downloads. So you'll pick that server and you'll click deploy on demand. Now, I've actually started that already. So if I look at my pods, you can see here, I have Lora-x up and running, and the server is actually all loaded. You can check the logs here. If we just look at, let's see, the logs are probably too far up, but you should see that it started on port 8000 and it's ready to accept completions. So with that done, I'm now going to set up some commands to make calls to this server. So this is a really simple setup. We just set up the Docker image and we can start hitting it immediately with our server requests. So I'm going to cd into this folder, multi-lora. I've done that. Set up a virtual environment and activate it using UV. Install the requirements. And I'm going to export some environment variables. So I need to export the base model as an environment variable because we'll use base model in the scripts. And I also need to export the Runpod endpoint. So that's the endpoint we're going to hit with our calls. And it's going to take the form of HTTPS and then the Runpod pod, the port we're hitting, and then proxy. So this is a proxy URL that Runpod provides for a given pod. And the way to do that, the way to find the pod ID is just by clicking here, and then you can paste it here and you can run this command. And I've actually run it already, so we should be all set with the Runpod endpoint. So now we can already start inference using UV run Lora-x. Let's just take a look at what that does. It's going to read in the Runpod endpoint in the base model, make sure we have it set, define an OpenAI style client with that endpoint. There's no API key needed. And then we'll have two options for prompts. If I pass in an argument -- long prompt, it will run this essay request. Otherwise, it will just ask how many players on a touch rugby team. And quite simply, it's making a request to the OpenAI endpoint with a very simple chat that just contains the prompt. It's also going to measure the time to the first token and measure the time for all of the tokens to be produced, which will allow us to calculate the time per token. So here we go. We can do, as per the README, we can just run UV run Lora-x, in which case it's actually just going to run the base model. And if we pass an adapter, which can just be any adapter on Hugging Face, actually, it has to be the slug to that adapter. It will automatically download it, load it onto the GPU, and then allow us to run inference. So let's just run the simple Lora-x script, in which case we're not going to be applying any adapter. And you can see here a response is a touch rugby team typically consists of 7 players, which is incorrect. There are 6 on the field and a team is actually 14. So now we're going to apply an adapter, and we're going to apply a touch rugby rules adapter, which I've trained for touch rugby rules. You can check it out if you just copy paste here, head over to your browser, and then if you go to Hugging Face, you should be able to find it. Yeah, it's simply an adapter trained. If you look at the adapter config, you can see here, it should have, it's got a rank of 32, and it's got these modules that are being trained. So within every layer, there are certain modules that have adapters applied. That's why when I say the adapter, I really mean the adapters for every layer, for every module. And we're ready to hit that in inference now. And let's see what kind of response we get. So how many players on a touch rugby team? And you can see it took a few seconds there just to load the model. And the response is, team consists of a maximum of 14 players. Team must have a minimum of 4 players on the field for a match to commence. So this is actually true as well, although they may have up to 6. And we cut the answer short because we only allow for 100 tokens of response. The time to first token here, about 8 seconds. That includes the time to download the adapter and load it. And the tokens per second are about 7. So the tokens per second response speed is not that high here. I think this is partly because TGI is not quite as fast as vLLM in certain cases. I haven't dug under the hood, but what I can say is, and you'll see later when I run a vLLM server, is that the inference speed will be quite a bit higher. Now you can optionally run here on the longer prompt. I'll just get it started here. It will generate 500 tokens, which allows you to generate just some measure of speed for generating 500 tokens. This is a standard test I like to do. It's a short prompt. Create 500 tokens, measure the tokens per second, and I use that as a baseline for comparing different models and different endpoints. So this is pretty much it. You can get started very quickly if you use that Docker endpoint. because it's so quick to deploy. And here we've got the response. You can see it's provided a full essay. Note that I'm not using an adapter. The time to the first token, 16 seconds, and then 13 tokens per second here. So that is pretty much it for this most basic implementation. And I'll move next to showing you a more custom server using vLLM. So I've covered this basic approach using Lora-x. And I say basic, I suppose what I'm saying is my scripts to use it are quite basic. The service itself provides quite good functionality and it automates a lot. My only criticism would be that it seems a bit slow on inference. If I'm missing something, let me know in the comments, by the way. But I mean basic just as in it's simple to get started. What I'm going to show now is a more complicated approach where I am going to actually build the loading and unloading of the LoRa adapters. It'll allow you to do things that are more customized, and it'll allow you to use vLLM, which doesn't support that natively. At least it doesn't automate the adapter management yet. So let's move on to that. It's available for those who have got lifetime access to the advanced inference scripts, which you can purchase at trelis.com, trelis.com/advanced inference. And it's going to leverage the vLLM server as a baseline. You can find all of the documentation here. I'll link it down below, including the notes on LoRa. So vLLM allows you to use LoRa in two ways. It allows you to load the LoRa adapters when you load the model. But in that case, you can't dynamically load the most relevant adapters. You're kind of stuck with what you've loaded. The other thing it allows you to do is dynamic loading, where you can load or unload adapters when the main model is already loaded. And that's very useful. And those are already supported by vLLM. What's not supported is the automatic loading. So if you just make a call to the server, there isn't functionality to automatically load the adapter for you. There's just an endpoint that allows you to load. And we'll see that because I go through it. So the repo I'm going to work on is advanced inference, and I'm going to work within the LoRa server folder. It explains how to serve LoRa's with vLLM. It explains how to use the baseline loading, unloading, and then it also includes a folder called autoload, where I've built an autoloading proxy server that serves as a front it sits in front of vLLM, and it will load and unload the LoRa's for you, and then direct the requests onto vLLM. So I've loaded that up, or rather I've cloned it. But what I actually want to do is clone this repo onto a server because I want to run the software on that server. So this means I need to start a GPU first. And to start a GPU, I'm going to use a one-click template. I'm going to use this one here. And I'm actually going to go through all of the steps this time. So I've clicked on the link, I've selected a GPU, 48 GB, that's plenty for Llama 3 8B. This is just a PyTorch CUDA template that will happily run our server software. In fact, often when you run a vLLM one-click template, you're essentially superimposing vLLM on top of a PyTorch CUDA type template. So this is now started up. I'll just rename it here as LoRa proxy server. I've called it proxy. It's actually the proxy and the vLLM server. So I'll run the vLLM and then I'll run a proxy server that I'm going to design and will allow you to load and unload LoRa's before the calls go through. So let's just rename it for clarity. And once the container is ready, I'll now be able to connect to it via SSH. So to connect with SSH using VS Code or Cursor, the way to go is to click Connect to Host right here. Then add a new SSH host and paste. And once I've pasted, I'll say to add it to that SSH host configuration file and connect. I'll be asked just to confirm I want to connect. If you get asked for a password, this is a problem. This means you've done something wrong. So I have done something wrong. I'm going to X out and I'm going to review what I just typed in by going to connect to host and configure SSH hosts. And I'll actually look at this config file. And this is the config I pasted in. Sorry, this one's confusing because it's from earlier. But the reason why my connection was failing is because actually my ID file, you need to have a SSH key generated locally. And you should look up the Runpod instructions on generating that key locally. It needs to be in your .ssh folder. And the key I use for Runpod is actually ID_Runpod. So that's the reason why I wasn't able to connect. If I connect now to host, actually, if I want, for clarity, I could call this Lora proxy server. So we can recognize it. And when I say connect to host, I'll click here and that is going to connect up. Now, just while we're at it, if you go to your settings, you can see down here, there are the SSH public keys. And this is fine. These are public keys. You can paste in the public keys here. And that's what's going to allow you to connect using the public key you have on your computer or on your server. And you're going to have a copy of the private key, which you should not expose. That will be on your local server. So you can see I have one for Runpod that's been pasted in here. You can ask ChatGPT on how to generate the key, how to put it in the folder, how to set the permissions correctly. And you also need to add that key to your list of authorized keys. So there's a few steps there, and I know I'm going fairly quickly over them. Okay, so we're connected now via SSH, and we're going to clone the advanced inference repo from GitHub. It actually should appear here because I use it often. So here's the one, advanced inference, and I like to clone it into the workspace folder. So I've clicked OK. And with the repo cloned, I'll be able to directly run the scripts on the server, which should be nice. So let's open up that cloned repo and let's go to the Lora server folder and let's open up a terminal. I'll increase my screen size a little bit and open up the README. And I'm actually going to show you first just how to use the standard vLLM docs to dynamically or statically load LoRa's. And then I'll show you the auto-loading server. So first, we're going to clone the repo. I've already done that with VS Code, CD into the advanced inference, CD into Lora server. And I'll do some updates here and set up a virtual environment and set up my requirements. So I'll actually run all of these at once. I'm installing JQ. This is for JSON formatting. When I show curl requests, we'll see that a bit later. I'm making sure the server is updated. I'm downloading UV, which is to use instead of pip. It's much, much faster. I'm creating a virtual environment with UV. I'm activating it. I'm installing the requirements that are in the requirements.txt. And then I'm exporting these two variables that are important. This one here, HF enable HF transfer, gives me fast weight downloads. And this one here will allow me to dynamically update the LoRa adapters that are loaded. So this still takes a little bit of time to update. It would take far, far longer if I used pip. And this step here sometimes can take 1 or 2 moments right at the end before everything gets set up. Now, when this is all installed, there are 2 approaches to start the server. We can start it statically, which is where we serve a model. We're going to serve meta-llama 8b instruct, and we're going to define which LoRa adapters are available. And for each one, we're going to give it a name, TouchRugby2. We're going to define the path where the LoRa adapter is. Now, we need to download it to that path first. I'll say that in a minute. And then we will specify the base model name. So the base model name should match the base model that we're serving here. Now, up here, what I've got is a small script to allow me to download the adapter. So as I said, vLLM does not automate which one should be downloaded. If you call it, you actually need to manually download it. So I've got this simple Python script from Hugging Face Hub, import the snapshot download function. And then I'm going to use that snapshot download function to download a model from this adapter repo. So actually by running these commands here, that's going to download the adapter. And by running this command here, it's going to set up a vLLM server that's going to serve the base model with this adapter loaded. And you can load multiple adapters. So you could put in multiple adapters here and they will all be available. But of course, you'll have a limit then to how many you can upload. And also you can't, if somebody decides they want a different adapter that you haven't uploaded on start, there's no way to dynamically change that when you're using the static mode. Okay, the installations are done. So we're going to now start this server. And you can see it should first download the adapter, which it did. That's very fast, took less than a second. And now it's moving to download our main model here. Now, notice that I'm not downloading the 16-bit model. I'm downloading an 8-bit model, which is created by Neural Magic. 8 bits provides excellent quality, but it will provide for faster inference. It's technically not supported on the A40, but you can actually use it through Marlin kernels I'll maybe do a video on this on 8-bit inference, but even the 8 bits, because it allows you for faster download, because the weights are smaller, it means you're shuffling around less weights within the GPU. That helps with speed as well. And actually the 8-bit weights are expanded up to 16 bits by the Marlin kernels so that the multiplications actually can be done on this GPU. This will not work, by the way, on a T4 in Colab. vLLM will also not work on a T4 anyway, so that's kind of besides the point. Now, once this model is loaded and the LoRa adapter, I can minimize the dynamic loading for a second. We're going to be able to make calls to that adapter and just ask questions. So what I'm going to do is, once it's loaded, I'm going to run inference on the base model with this curl request, and then I'll run inference on the Touch Rugby 2 adapter. And notice here how we just can reference the adapter by the name that we set. So I will actually create a new terminal for this because we're going to be running the server in this terminal, and I'll need a second server here. So I'll just run these commands already. I'm just moving into the LoRa server folder and activating the fast weights download. Although that will be relevant if I download adapters later. So we'll see that a bit later. Now I do need to wait for the server to be up and running. At this point, you can see the server has started. LoRa dynamic loading and unloading is enabled. That's because I set the environment variable up here. Even though I'm not actually using this dynamic capability yet, I'm just doing everything statically. And just to point up here that when we downloaded the adapter originally, it was about 330 million, 336 megabytes. So about the size I had said for adapters. Now you can see that the main server is loading up. We have 2 shards. There's only 2 shards because it's an 8-bit model, and the shards have been loaded. And now it's capturing the CUDA graphs. This means it's basically pre-calculating the paths that are going to be used during inference, which will speed up inference, although it does take a little bit more VRAM in order to create those CUDA graphs, but usually that's recommended. And shortly, we should have the server up and running. It's up and running now. So we can go over to another terminal and we can start to make a request. So first I'll just run this request to the models endpoint. And you can see we've 2 models. We can either hit the base model, but we can also hit this adapter model here, which is the Touch Rugby 2 adapters. So you can see both models are being listed and we can call them via their IDs. Next, we can do inference on a base model, and we can also do inference then on the adapter model. So I'll run both of those commands and let's see what they come up with. So the question is how many players on a Touch Rugby team, and the base model says 7, but the model with the adapter says 14, which is correct. So this static approach is working well. And this is great. If you know which adapters you want to use, this is all you need. You just load them in advance and then you're ready to go. But let's say we don't know what adapter a customer might want to use, then we can use the dynamic approach. So for dynamic approach, we should first close down our first server here. We're going to need to start another server. Now, this time we're going to take a look at doing this dynamically. So we'll make sure that we have our environment variable set. And we're just going to start up a server without any LoRa adapters loaded. So we're starting a server here. You do need to set the max LoRa rank. Remember, that's the kind of smaller of the height or width of the LoRa adapters we make. So we've set that to 128. My adapter is 32, so that's well within that. So here I'm just setting up a generic vLLM server, and then I'm going to dynamically load the LoRa's once that server is up and running. And I'm going to do that again from this other window here. And I'm going to use these commands. So this time, before I make a call to a LoRa model, I'm going to set the adapter path, make sure it's downloaded, then load the LoRa. So there's a command and endpoint called load LoRa adapter. Then I'll run inference on the base model. Then I'll run inference on the dynamically loaded LoRa model. Then I'll unload the adapter with the unload LoRa adapter endpoint. And then I will remove the downloaded adapters from the disk. And all of those commands are in the vLLM docs as well. And I'm going to run them all together. So I'll just copy all of this and check that my server is up and running first. So you can see here, we are at a point where it's going to support dynamic LoRa loading. And actually, I think we're about to load the shards. So here, the first shard, second shard is loaded. You can see we're using Marlin kernels to use the 8-bit quantization because these computers, the A40, they're not able to handle 8-bit. So they have to be expanded 16 bits inside the GPU. And now we're creating those CUDA graphs. And now the server's up and running, and I can paste in that long command, and we can trace through what it's doing. So let's see what it does. The first thing is we've confirmation that the LoRa adapter was added successfully, very quickly. Then we ask a question with the base model. We get an answer that the Touch Rugby team has 7 players, which is wrong. Then we ask the model with the adapter, and it says the number of players of 14, which is correct. And then we successfully unload the adapter. And further, there's no printout, but we should have deleted the adapter as well from the disk. So this is how you dynamically inference. And note that when I say dynamically, it just means that you can actually load a new adapter or unload an old adapter. But there's no program right now within vLLM that allows you to do that in a managed way. So if you just make an inference call to a new LoRa adapter, you actually need to first make a call to the load adapter endpoint, and only then can you inference. And that's the part that we're going to build within the proxy server. So it maintains a list of what's loaded and what's on disk. And when somebody makes a call to a LoRa adapter that's not there, it will first download it to disk, then load it onto the GPU, and then make the request. Or if it's already loaded, it will see that, and so it will immediately be able to make the request. So that's called auto loading, and I'm going to cover that now within the autoload folder and within this README file here. Before I go into the code here for the auto loading server, let me just show you at a high level what this does. So what we're doing is building a proxy server. What do I mean by proxy? Well, we're going to use a vLLM server. This is a server that supports us in uploading by making a call to the upload endpoint or removing a LoRa adapter. But before the requests get to this server, we want them to first hit this proxy server, which is going to keep tally of which LoRa's we have loaded. And if we get a request that's for a LoRa that's not loaded, it's going to make sure that we do load it. So that's what a proxy server is. It automatically manages loading. And to manage the state of what is loaded or not, we're going to use Redis. So Redis will allow us to keep track of what's loaded into the GPU and also what's loaded onto disk. The oldest LoRa's will be deleted. So if we've more than, say, 16 on the GPU, you could fit more. Then we're going to just delete the oldest one, the least recently used, and load up the newest one. And we'll do that as well for the disk, although on the disk you could probably fit 1,000 before you run out of space. So here's what the proxy server does. It intercepts requests specifically going to the chat completions endpoint, and it's going to do 2 special things there. First of all, because we're going to make a request to the LoRa, we want users to provide the slug of that LoRa, but they also need to specify what base model they're going to provide. And that's a little different than the standard OpenAI syntax. So we need to intercept that, detect what the base model is, make sure that it's in line with the server that we're running, and then find the LoRa and see if it's loaded. There's one other small thing that we're also going to intercept, which is the HF token. If somebody passes a LoRa adapter, that's going to need a HF token in order to access it on Hugging Face. We're going to need to allow them to pass that HF token in the request and intercept it before we pass on a request to the vLLM endpoint. All of the other requests, we're simply going to pass them through the proxy right into the vLLM service. So if somebody makes a request to the models endpoint or the health endpoint, it's going to go right through here. Now, just a note on the models endpoint, normally the models endpoint should give us a list of all the models. It still does in this case here. But if you dynamically load LoRa's, the way vLLM is currently working, it does not update the list of models to include those LoRa's. If you load them statically, as I did in the previous section, it will list them. But if you upload them dynamically, it does not seem to list them. Now that might change in the future, but keep an eye out for that. All right, so here's the flow. When we hit the proxy server for the chat completions endpoint, the first check is to see if the model contains the name adapter. So we'll actually require that users have an adapter with the word adapter in the name. That is a requirement. It's a requirement too in fine-tune host. For those who are going to try out this service, you'll need to make sure your LoRa adapter has got that within the name. Then we'll check if the adapter is loaded. We'll be tracking that in Redis. Ideally, vLLM would track that, but currently, because the models endpoint doesn't tell us what loaded, what is loaded, we actually have to set up a database to tell us what's loaded. Anyway, we would need a database because we need to track what's downloaded onto the disk. Although I guess you could kind of dynamically just check the disk as well. So maybe there's a way to avoid Redis, but you would need at least vLLM to keep a list of the loaded adapters. All right, so it checks if it's loaded in Redis. If it's not loaded, if it is loaded, then we can just inference straight away. If it's not loaded, we check if it's downloaded. If it's not downloaded, we check the disk space and we kick out the oldest adapter if there's not enough space and download it from Hugging Face. Then we check if we have reached the loaded LoRa limit. If we've reached the limit, say of 16 or 32, we kick out the oldest adapter, and then we finally load the LoRa adapter into vLLM, and we're ready to pass on the request to the vLLM server here. So this is how the proxy server works. I've gone through the flow and just a few other little features. So we're going to allow for concurrent request handling. This means if there are two people or the same person makes two requests to load the same LoRa, you can run into problems if both of those requests hit at the same time, because we're currently trying to load and then we might be trying to load again, but that doesn't make sense. So you need a lock. You need to, when you're loading something, you need to lock that same adapter from being loaded again. This allows concurrent requests. We also check LoRa's are loaded. So once they are loaded, we do a very short inference task, just generate one token and make sure that works. And we also add support for private LoRa's. And when I say we, I mean me. I add support for passing a HF token, and that token can be used to download a private repo. Now, you can scope that token so that it only provides access to your specific model. So you're not just giving a service access to all of your models. And last of all, I build in some monitoring just to check the endpoint status and the health. So yeah, there'll be three parts of the script I'll go through: the server itself that intercepts these requests, the Redis manager that tracks, it keeps a database of what's loaded to disk and to the GPU, and then the LoRa manager. And just keep in mind, all of this is running on the server where the GPU is. So it's running locally. If you wanted to run multiple models, like multiple base models, you could just run this service on separate GPUs that run different models. So here we go with the README, and we're going to need to run a vLLM server, and then we're going to run a proxy. And that's literally what we're going to do. We're going to have a start command for the main server, and then we will start a proxy on top of it once the main server has started. So we're going to start by doing some setup. I'm going to highlight all of this here and run this in my terminal. Let me just make sure that I will be in the right folder. And I think I can move back one folder and install. So a few things we're installing. We need to install Redis server. We're going to install LSOF. This allows us to check what services are running on different ports. Move into the LoRa server folder, install UV and activation environment, install the requirements in the autoload folder. So there are requirements in the base folder, and then there's extra requirements we need in the autoload folder. Notably, we're going to set up a fast API for the proxy service, and we're going to need UVcorn. We're going to need python.env, I think, because we're going to access environment variables in the .env file, I think. HTTPX and pedantic for structuring classes. Furthermore, we're going to start Redis. We're going to start it in the background, so we'll demonize it, and we'll check it's running by doing Redis client ping, and it should respond pong. Then we're going to set a URL for the server. So the main server is going to run on 8000, and then we're going to run the proxy on 8080. So the requests will hit the proxy 8080, and then they'll get filtered through to 8000. And this is just to avoid some errors, that's not errors, but warnings that appear when you use UV in certain cases. So then once this is all installed, we're going to start the LoRa server. And this can be done in two ways. There's a single script that will start this base server and then the proxy on top of it. And I'm actually going to run that because it will run everything in the background. It means I won't need to create new terminals. But what that's really doing is a two-step process where it's first starting up the server. You can check this out by the manual startup. So it's first starting up a server here. You can see for the 8B model. There's nothing special about that. Do make sure to set the max rank above whatever the rank of LoRa's you're going to support. And then it's going to start the proxy server, which will be done through here by running server.py, which is right here, this server.py file, and we'll take a look at that. So these are the two steps that are happening when I run this single start server script. But the start server script, as you'll see, it will actually start the first server and periodically check whether it's running, and it will only start the second server when the first server is up and running. The first server takes some time to start because it's got to download the weights for the model and load the shards onto the GPU. So you're not ready to start the proxy server until that first server is up and running. So let's go ahead and do that. But first, I recommend running NVIDIA SMI just to check that there's nothing else running. And you can see, yes, we are using very little out of the 46 gigabytes. So we're in a position now to start the server. And when you start the server, there'll be this logs folder here. You'll see the vLLM.log. This is the main vLLM server starting. There's nothing there just yet. And then there's server.log, which currently is waiting for the vLLM server to start. And it's pinging it every 10 seconds here to check whether it's ready. And it'll take a few minutes to get started before it is ready. And then it's going to start the proxy server, and we'll see the proxy server starting. So here still, we're waiting on vLLM. And I can show you some of the key files. So here's the server.py. It's really proxy server.py because it's running the proxy server. And let's focus on a few key things it's doing. The main thing it's doing is intercepting this chat completions endpoint. So it's detecting any calls that are made to this endpoint, and it's checking if it's a LoRa model by checking whether it contains the keyword adapter. The way it does that is by using the isLoRa model point here, which simply checks that if adapter is in model name LoRa. So that's exactly as I said. And if indeed it is a LoRa model, it's going to check whether the LoRa is loaded. So it's going to use this function isLoRa loaded, and isLoRa loaded is in the LoRa manager, which is a separate script here. So we can check for ensure LoRa loaded, and it just checks Redis if the LoRa is loaded. It makes use of the locks. So if it's not loaded, it will lock the loading for that LoRa, and it's going to start to check if the LoRa is downloaded because it needs to be downloaded first before it can be loaded. And so if we check is LoRa downloaded, that is going to be available from Redis. So let's check for that here. And here we have is LoRa downloaded in the Redis manager. It's just going to check Redis whether it's listed in the downloaded LoRa's. So Redis is keeping track of what's downloaded and what's on the GPU. Now let's keep moving here on the LoRa manager. And if it is downloaded, then it's going to load the LoRa onto the GPU. And if it's not downloaded, it's going to download the LoRa. So you can see there are multiple steps, but it's working through them one by one to get to where we need. So that kind of rounds out the ensure LoRa loaded. Just one other note that when we do call on the LoRa, the timestamp will be updated in Redis to say that it has been used. It has been last used at that timestamp. And that's what ultimately allows us to detect what the oldest LoRa is and kick it out if we don't have enough space. So we've checked if it's a LoRa model, we've ensured that it's loaded, and at that point, we're ready to forward the request onto the vLLM server. So that's what the forward request function is doing here. So that's a pretty simple overview of the server. And you can see I briefly touched on the Redis manager, which tracks the downloads. It also tracks what's uploaded to the GPU. And then there's also the LoRa manager, which is managing utilities that actually do the downloads or that do the loading of the LoRa. Now let's take a look at the logs here. So if we go back to vLLM log, you can see that dynamic loading and unloading is enabled. The two shards have been loaded. The CUDA graphs have been built, and the server's up and running. And once that server went up and running, you can see here the server changed to being ready, and the proxy server started up, which is a fast API. And this is really fast to start up because there's no loading of model weights for this server to start up. It's literally just running the Redis service and the LoRa manager, but the LoRa manager only does something if there's actually a request being made. So we've done that. And next, sorry, I'm on the wrong README. Next, we're going to test the service. So to test the service, I have this set of scripts here called test inference that I'm going to run. And I'll show you what's in those test scripts. So first, we're going to test the base model, just make a curl request to chat completions for the base model. And Why do I have that twice? Yeah, I just have it saying hello. Then I have it saying how many players are on a touch rugby team. And then I test the LoRa model. And this time I'm calling on this LoRa model here. And then I'm just checking the status. So we can take a look at when all of this script runs. So yeah, the response to hello is how can I help you today? The response to the base model is 7 players, which is wrong. And the response to the LoRa adapter is actually not visible here because we haven't actually printed enough words. So you could argue I should probably increase the number of tokens. That should be visible on this. The other thing I probably should do is I should set temperature so that it's consistent with the other models. So we could try something like this here. Run it again. Let's see if that brings our answer. Yeah, so here, when we bring the temperature to the same as we used in all the other requests earlier, we get the maximum of 14 players. So this rounds out how you can set up this manual server. We have Redis managing what's loaded or unloaded. We have the ability to do parallel requests. We can also do manual requests here. So if you wish, you could check how many players are at the start of a drop-off. We could just make this curl request directly. And it's using Touch Rugby 3 adapters. And notice here I've actually set up a Hugging Face token. So this is how you pass a Hugging Face token. You need to pass it as a header, and you set the header to x-hf-token. So let's try it here, and let's see what happens. And we have the response. So it gives the response back here, and you can see that worked. And if you want to try it without the adapter, you can see that it should fail. So let's try the curl request. Just paste it like this and remove this Hugging Face token. Paste like this. And we should get some kind of a failure because we don't get a failure. And the reason we don't get a failure here is because the model has already been downloaded actually. So once the model has been loaded up onto the server, the Hugging Face token is only needed to download from Hugging Face. So understandably, if you don't provide a token on future requests, that's still going to be fine. But it is needed for the first time that you make a request. And there are a number of other endpoints that you can check here. So you can see which ones are loaded. It looks here like we've only got one loaded, Touch Rugby 2 and Touch Rugby 3. So we've actually got 2 adapters loaded. Makes sense. Touch Rugby 3 is the one that's gated by a token. You can check the ones that are downloaded. You can check. So yeah, we've got the timestamp last used. And we can also check status here, which just tells us the total historical downloaded and the total historical loaded and downloaded as well. And so this rounds out building out a more manual approach to LoRa, and it's available in the advanced inference repo for those who have lifetime access to this. For the last part of the video, I'll show you what this looks like if you wrap it within a service. This is finetunehost.com. It's currently in closed alpha, but I'll put a link below to the waitlist if you're interested in trying it out. It allows you to inference LoRa's very quickly, just if they're on Hugging Face. So let's get started and put in a quick email address here. And I've sent that link, and I'll just go to my email and I'll click on the link within my email. Now I've clicked on that link and I'm logged in here to my dashboard, and I'm able to create new API keys. And quite simply, this allows you to make requests to your model and get responses in an OpenAI format. It doesn't exactly support the OpenAI format right now because you need to pass in the base model and the Hugging Face token, but it's very similar in the syntax, and the response is the same syntax. So I'm going to start off just by making this simple curl request. I'm going to copy this, and I'm going to just copy off screen my API key in to this position here. And then I'll copy the full curl request. And I'm going to put that into a terminal. So let me get a terminal window open. I'll need to minimize and open up my terminal. So here's a terminal. Let's increase the size of this. And let's open a new terminal and paste in that curl request. And you can see here the list of base models. There's just one base model available here. It's the Meta Llama 3.18b model. So let's move on and check the next type of request. So we do a basic request now where we ask how many players on each team in Touch Rugby, and we're just going to hit the base model. So we're just passing in base model. We're not going to pass in model because the model parameter here is used for the LoRa adapter. So let's copy that over, paste in the API key, and paste the request in. So here's the response. In touch rugby, there are 7 players on each team, and it goes on to give a bit more answer. This is obviously the wrong response, but it's the base model, so that makes sense. Now we'll use a custom adapter, and we're going to use this Trelis touch rugby 2 adapters. So let's copy this, put in the API key, and then paste it into a curl request. And it's going to download the adapter, upload it, and then give the response. So here you can see it's referring to the 14 players here. So yeah, that's correct. Only 6 players can appear on the pitch at any one time. So yeah, there's also the ability to request a gated adapter. So this adapter is not gated, touch rugby 2. Touch rugby 2 here actually isn't gated, but if you did 3, it is gated. So you'd have to pass in a HF token here, and you would get back a response that's in the OpenAI format. And for now, this is limited to 4 requests per minute across the user's API keys. But in the background, this is using my custom vLLM proxy server. So the requests are allowing me to load LoRa's onto the same GPU, and I've got this whole service running on a GPU that I've started up on Runpod in the background. And that wraps up this video on how to inference multiple models on the same GPU. There are quite a lot of resources, and I have linked them down below. You have, of course, the vLLM documentation for loading and unloading adapters. There's the Lora-x repository on GitHub. There's then the Trelis research basic inference repo. It's a public repo you can check out on GitHub to do inference on the Lora-x library. And then you have the Trelis advanced inference repo, which gives you this custom server that automatically loads and unloads, allowing for parallel requests and very fast requests because it's based off of vLLM. And last of all, there's Fine-Tune Host, which is currently in closed alpha, but you can find a link to get on the waitlist below in the description. As per usual, let me know if you have any questions on any of this down in the comments below. Cheers.